Computer. Hey, hi everyone. Thank you so much for joining the design feedback call. The idea of the call is to have all of us present our respective machines at this point so that all of us can give collective feedback to each other and run through it a little bit in more detail, 1:1. And that was the whole idea of the call. So wanted to take about 4-5 machines at the time. I've also shared the construction data form. If all of you can fill that out, that'll be really helpful for others as well. While of course, we're also working on the other form where we can take more output and testing data as well. But at this time, the idea was to sort of just have a collaborative conversation in depth for each machine. And that's why I'm going to just pass it on to Anol and Vaibhav. I think Simran, I have your data. So maybe you want to take us through your machine, but just give me a second before I pass on this to Anol and Vaibhav as well. So just 1 second. Yeah, there you go. Sorry, could you guys hear me? I couldn't hear anyone actually. Hello. Were you able to hear me? Sorry. Hello.
Yeah, we can hear you.
Okay. Were you able to hear me before when I was speaking? Was that okay?
Yeah, the whole time.
Okay, cool. Simran, 1 second. I'll just pass it on to Anol. Yeah. Okay, you want to take us through your machine, Simran?
Right now it's not running. We're doing some troubleshooting on it, but I can still walk everyone through it.
Yeah, that'd be great.
Okay. I think I'll just switch to my phone. So just add me there once I send the.
No problem. Yeah, we're recording this. Yeah, go on.
Yeah, just 1 second. Okay, so I'm just using my laptop, so like bear with the angles. So, well, actually, just give me a second. I'll just get the phone. It's better. Otherwise, I won't know what I'm showing.
Yeah, let him send the request.
Okay, looks like you need to download an app for that, so I'm just not going to waste time on that. Browsers in your app. Okay, so I'm going to ask close to the 8-volt circuit on the right. Okay, let's see what we see here. So this is our setup we have here. Well, this is really difficult. Does anyone? I know, but they have to like download it now. Does anyone else want to go before us? I'll just set up the thing.
Yeah, let somebody else go, and then we'll figure out if we can download the app.
Okay. Yeah, we'll do that. Thanks.
Oh, Krishna, actually, Krishna, you want to go next?
I'll get him on.
Hey, okay. Yeah. Hey guys. So here as well, like I don't have a working machine because one of the filters blew up. So it can zeolites. So I'm like kind of arrested it, but I can just walk through it. But yeah.
Sorry, what blew up? One of the sieves blew up or the filter?
No, the filter inside the sieve.
Okay. The one which is going into the sieve.
No, at at the input, yes.
Input. Okay. Wow. How did it blow up? What happened?
Yeah, it was like an explosion basically.
Oh, wow.
Yeah, no, actually what happened, like I put 2 compressors in parallel and the pressure gauges was at one end, which I couldn't see. So I was like opening, and then before I came and saw, It exploded.
Wow.
1 second, guys.
Hello.
No injuries, I hope.
No
I'm sorry,
injuries.
what, Arun? Yeah, I'm sorry. What?
No injuries, we hope.
No injuries, but just that the zeolite just hit on my face when I tried opening the exhaust. So it was like 200 grams of zeolite just hit on my face. So
Oh my God.
Wow.
this, carcinogenic and everything was like, I don't know what to say. Anyways,
So safety goggles is the must.
Yeah.
I used to do it while transferring the zeolite, but this was like kind of unexpected. It's like, yeah. Anyways, so this is a very jugaad setup right now I have. So I have a compressor unit in there, like a tank compressor, I mean, with the tank. That one.
Yeah.
And then I also have this. Okay. Yeah. I also have this compressor, and basically it's going parallel, and I'm using like a bucket of water for cooling, and it really is actually working. The cooling part. And then I'm using this hydrant moisture separator, and then it goes to an FR unit, and then it goes to a charcoal, like an activated charcoal filter in there, that one.
Okay.
So with this, I'm able to achieve like less than 12% humidity. Okay, and then it just goes to the walls, which is like kind of messed up here. So basically, it just goes to the wall, and I use these RO canisters, 20-inch length canisters. But what is happening is these RO canisters is kind of leaking here. Now you can see these joints, right? I used like a silicone gel sealant, but then because the pressure is very high, it's like 2.5 bar to 3 bar per sieve. So it's like kind of making holes through the silicone gel. So I'm having a major leak there.
Doesn't have an O-ring.
Yeah.
Yeah, it doesn't have an O-ring over that. Have you tried using an O-ring?
Yes. So it has an O-ring inside. It has an O-ring on the lid as well as on the bottom, like, wherever it couples. But still it has like a leak, pressure leak. So basically what is happening is even though the sieve has like 2.5 bar, like at the output oxygen level, it's less than 1 bar. It's like around 0.75 bar is what I'm getting. So yeah, I mean, although I have like a surge tank and all,
Okay.
it goes to surge tank, but then I'm not using an orifice. I'm just using these flow control valves. I'm just using 3 of these flow control valves adjusted all equally by hand. Yeah, that's it.
So it looks like the RO canister might not be a good way to.
Yeah, exactly. That's what I think so. Because actually, as per the Jamboard created by Abhimanyu, right? Like, and you guys have added it. So as per that, I see that most of those who got 95 plus percentage, I'm getting a similar rating. I'm getting like 2.5 bar and 2.5 bar per sieve. All that is working. But then still I'm getting only 70%. So I suspect this leak to be a major cause of that, is what I think. But if guys can suggest something.
We had similar issues with the PVC sieves.
Yeah.
Either they were forming leaks or there were gaps inside that were not allowing the pressure to reach at that optimal point where we were able to not get the zeolite to compress enough, perhaps.
But Vijay is using the same PVC, UPVC stuff, right?
Yeah, we were using the PVC stuff, UPVC.
No, Vijay.
Vijay, yeah.
Vijay is using the UPVC.
Is the last one, the final one, is he using PVC?
Yeah,
he's still using
he's
PVC.
still using.
He's still stuck with PVC, yes.
Yeah. So we'll have to check.
We've moved to aluminum canisters, as you know. Yeah.
Yeah, but then Vijay has, I don't know what he's done with the system, right? He has a couple of different specifications that he's running inputs and outputs at, right?
No, pretty much using PVCC. So like very different over there for sure.
So his gluing mechanism is better. Is that what it is?
No, doing the same thing as us.
Okay.
No, he's doing the same thing as us. He's just one of the things that I know is he's been cooking a zeolite. And the other thing is that I think his compression has been.
He's got a better vacuum pump.
He's got a better vacuum. He's got an industrial vacuum pump that's helping him compact the zeolite.
Compact the zeolite. So that I think helps a lot for sure.
Fair.
Okay. So I also managed to buy a industrial vacuum pump. Just that I haven't tried to compress it with it, and also I don't have a compression spring inside. That is also something happening.
So how are you compressing it?
No, I'm just filling it till the top, and then I'm using like a thermocol sheet to kind of fill that empty volume inside the lid.
Why doesn't he use the Scotch-Brite and the steel wool?
Oh yeah. So
Because right.
We've been using his Scotch-Brite and steel wool instead of the compression springs. So we're not using compression springs anymore.
Okay, so it works for you.
Yeah.
Okay, basically, still the shops have not been open. The lockdown has been extended in Tamil Nadu, so that's the reason I couldn't even buy those Scotch-Brite things.
Oh wow, that bad.
That should be easy to find.
But
no?
that's essential
But
supplies,
like,
no?
that should be at any grocery store you should be able to find.
No, I mean, right now there's no grocery stores. We have only vegetables sold in trucks. So that's the only supply of.
Oh wow. That's really bad.
Damn.
So we don't have any shops open.
Have you tried Amazon?
Amazon?
Oh, come on. No.
It's not coming. Actually, it's not going to Tamil Nadu anymore.
Wow.
Oh,
That
wow.
is a bad scene, man.
Yeah.
Well, I guess you guys will recover the fastest compared to the rest of us.
Hope so. Let's see.
Yes.
But yeah, is there any other alternative for springs or Scotch-Brite or anything else?
Not really. I mean, you have to compress the powder for sure. I mean, that is essential.
Right.
Like even the Chinese seeds you opened, they were pretty
Yeah.
tightly compressed.
The Chinese seed we opened were super tightly compressed and like perfect lattices because when we took out the material and put it back in, the same exact stuff, we couldn't fit it back. It was that much compressed. It was like literally both of us were on top of the tables trying to put as much as possible.
Yeah.
But it was humanly not possible to close the sieves with that much zeolite that they had put in.
Okay. And how do you pack the zeolites with the vacuum pump? Have you tried it?
With what?
With vacuum pump.
We put the vacuum pump
With
at the
vacuum. Okay, but then won't the zeolites leak through the filter because of the vacuum? How do you stop it from?
Scotch-Brite is there to.
Yeah.
Oh, okay.
And the N95 filter or whatever you use.
Yeah.
Okay.
Okay, right. Got it.
We can show you what we
do.
do.
Yeah, we have the Scotch-Brite, we have the stainless steel mesh.
Yeah.
So that's enough to prevent any
Drop.
Yeah.
By the way, anyone else has any comments on this? I mean,
Yeah, I mean, you guys can unmute your mics and speak up. I mean, there's something on chat. What's happening?
How can we look at this setup data?
Okay, you have a link.
Setup data.
Hi guys, this is Rajat.
hey Rajat.
I'll switch on my video. 1 second.
Okay, I can just show. I think Krishna is
Share
still.
the link on it.
Yeah, can you see me?
Yeah.
Yeah.
So like there's using that link, I can like enter the data, but how can I look at the data?
Yeah, I'll share the shareable view once you fill it out now. So I'll just share this shareable view as well.
Okay. I'm in the process of filling it. It's quite long, to be honest. So
Yeah,
I'm halfway there.
Yeah, it is.
It is a little bit of a longish data, but I think it'll be useful. So I'm just sharing this shareable view link with everyone where you can see other people's data as well.
If you guys don't mind, then we can go ahead. I have the phone ready.
Yeah, yeah, go ahead, Simran.
So,
Okay.
Dverse was Chennai, right? Very similar based on.
No,
Similar.
we're in Hyderabad.
You guys are T-Works, right? Hyderabad.
Yeah. Hyderabad. Yeah. Okay. So basically, I start here with our compressor. We have this stand. I think it's a 400 watt compressor, and it gets us to about 1.72 bar of pressure. For the moisture, we've created this canister, which is part of our canisters for the zeolite. We just stuffed it with alumina beads,
Okay.
and so that seems to work for us. We had the cooling coil attached earlier as well. So yeah, this is the alumina bead.
Pretty big particles.
Yeah, how big are these?
So 3 to 5 mm.
Oh wow.
Wow.
Yeah. So yeah, then so from here, we take it to these two 3x2 solenoid valves here. So this is what our initial oxykit setup is. From here, we've custom made. So ours is a mix of aluminum and PVC. So we have the PVC for the cylinder, and then we've custom CNC flanges out of aluminum, which are held with these threaded rods. We also have some O-rings on the inside, so that creates a nice pressure seal. Then on top, same thing on top here. We have our gauges.
Yeah, that's pretty solid top. Right?
Yeah.
Okay. We also just changed the circuit a little bit. So we'll just just show the gist of what sort of equipment we're using. We have our 2x2 valves here. We also made these custom. So these are our custom orifices, where we've taken a cylinder of aluminum. Oh, sorry, stainless steel. And then we've created there's a 5 mm long, 1.6 mm diameter orifice in the middle. So this allows us to put these 10 mm connectors easily on the orifices. So then, yeah, that's one way. We have our buffer tank here. This is again just a standard, I think, copy from the oxykit version. We have our pressure regulator. Then we have our rotameter. We also have a flow meter just to double check. And then finally we also recently got our oxygen sensor. So, and then we have our electronics, all boards over here. So that's sort of a setup here right now. So as I mentioned in the thing earlier, we weren't able to really get the oxykit version up to anything past 60%, like times and all we tried, but then we tried this a little more complex circuit with the 8 valves, which can be simplified to maybe 4 with a 5x3 valves. So that I think should work, and that worked to get us 95%. Trying to see what is wrong with the oxykit version to really.
Can you share your data for your flow sensor?
So data from our flow sensor right now, we're not logging anything. You mean like
model
what?
or make, the model or make that you
Oh yeah, it's a Festo.
Just give the model number, no?
Model number is. Have a look here.
Yeah, just keep it.
Just keep it there.
Yeah.
Okay.
DE73734.
Yeah, we got it.
Okay. So yeah, that's what we're using for that. Anything else you guys are interested in?
No, so what did you say that you did for 95%, which was different from the oxykit version?
Yeah, so basically, as I've shared on the group as well, basically that video is what we found worked. So if you look at here is the circuit, like this is just, again, the video is probably a better reference. So over here we have basically more valves that control the pressure in the canisters much more precisely. Like you don't have to always release exhaust with. So basically you have 2 solenoids here, two more here, and then this is one on the bottom, which is our equalization valve. You also have one on top. We had an orifice as well as a rotameter in series, because the orifice itself wasn't giving us, I think it got us to around 80%. But then when we added a rotameter and then reduced the flow, we could get all the way to 95%. And then you have two more solenoid valves on top. So basically what these extra solenoids, what they do, especially these top ones here, is that they allow the cans to pressurize in the first cycle. So here we have like basically our firing sequence for our solenoids. So we have step one, we have a pressure build stage. So we don't have this S4, S7 open. We just pressurize this up to whatever 25 psi. And then in the next step, we open this. And that really makes it like, that just allows us to get that pressure swing.
Interesting.
I mean, we have all of our cycles like sort of illustrated, but that's a lot to go through. But basically, I think more than these pictures, if you look at the video, which is by Mega Air, that really has like the whole, like we literally looked at that and simulated that with our system, and that seems to be the only thing that works for us right now.
LPM, they got it. 95%.
What's the LPM?
Sorry, what?
What's the LPM that you guys are getting?
We've only tried on 5 LPM. We actually didn't go past. We didn't increase it past that, but we could go up to 10. I think the compressor is able to give us 10 LPM.
You're using a pretty small compressor.
Yeah, you're using a pretty small compressor, right? 450
Yeah,
watts.
can we get 10 LPM with the compressor with all this? Yeah, it is a small compressor. We are aiming for 5 LPM really. So okay. 5 LPM, we're pretty happy.
Okay.
And so 5 ampere, so that's going to be the inlet.
No, the outlet.
No,
The
5 LPM is going to be the outlet. There's going to be that small compressor.
How much is
50
the pressure that you're keeping at the inlet? Like in the sense your tank?
So we are only able to get around 1.7 bar. That's because pressure drops, like especially the desiccant was is a big pressure drop. Before that, we were able to get around 2.5 bar, but with huge tank of desiccant, that really drops our pressure to 0.7 or 25 psi.
And what about the pressures of the sieve tank?
The sieve tanks, they the same. They reach up to the, like, because they're part of that same pressure region, right? They're on that.
And
But the issue is they don't swing. That's what we know is our problem. We just don't know how to get it to swing. And it used to swing with the 8 valve circuit. So we know that if we can get both are, like one is 0 when the other is pressurized, we know that it'll work. It's just that in practice with our oxykit circuit, it's sort of just like a stage between 1.5, 1 bar, like even how Ankit had described it in the engineering group.
what zeolite are you guys using?
We're using that LIX the JLOX 101.
So you're using lithium, right?
Yeah.
And lithium, and what is the granular size? 0.4 to 0.8, or is it bigger?
No, 0.4 to 8.
And do you guys have access to a good source of it at the moment?
I mean, we got it early on last, beginning of the month from.
Okay.
I mean, we got 10 kgs just to
test.
Yeah, just to test. But I mean, so that supply chain, I don't know how it is.
Fair.
How to,
So do you guys have any inputs for what Simran's asking?
I mean, I haven't studied the multi-valve version, so I think it's going to take some study to figure out what's happening with the pressure swing on that for sure.
So yeah, we're interested in is to get that circuit which you were talking about for the LIX, where you've removed the orifices and all that. Like, I mean, we're really open to just try, like whatever you guys have come up with, and we've been experimenting a lot with the 3 valves, with the oxykit, trying different sequences, different firing times. Like we've just done over the last week, we've just done a lot of experimenting with no real good results from the oxykit version. But yeah, so that's where we are right now.
So at this point there were 2 valves, right? Just 2 valves. We remove the whole halo.
Yeah.
There's no orifices, nothing.
Could you explain that to him?
Yeah. So what we've done is that we've removed the entire halo. We don't have any orifices. We don't have any equalization valve. We don't have any valves on the top. So literally what we're doing is we have two walls at the entrance, which are sort of creating pressure swing, left and right sieve. And on the outlet is just straight out into the surge tank.
Yeah.
We're
Yeah,
not
but-
using,
You have a T-joint and then the surge tank. That's it.
you're not even using one-way valve, nothing, straight out.
So you don't need equalization circuit in that. And these are 3x2s on the bottom.
Yeah.
Yeah.
So okay, I mean that just sounds very like, I'm glad it's working for you guys, but I don't know how it would work for us. I feel like we would still run into that issue where the two tanks just keep pressurizing and then they don't release the pressure properly. So we were also wondering whether our valves are an issue or
Timing
whether
cycle over there.
right?
So our timing cycle is like a 4-second cycle. But, we are using about 100 milliseconds for equalization.
Let's bring it over here. So our timing cycle is
Around 4 to 5 seconds. And I think we are using 100 millisecond for the purge and the other cycles, but that valve is not connected at all. So what we get is an overlap between the two valves that are going on and off. I think we can show a lab view capture of that later.
I think the best thing you can do for us so that we state your circuit is I mean, now that you explained it, I know what your pneumatic circuit looks like, but just for everyone else's reference as well, if you can just draw a very simple pneumatic diagram and then just the solenoid firing sequences and the times.
Right.
These three, and that's enough. Like, I mean, the main model of all the valves and all that don't make as much of a difference, maybe as just being able to.
Sometime later today we can do that.
Yep. We can
So
do
yeah,
that.
just simple diagrams, the firing sequence and the times.
Yeah.
We can give it a try. Hopefully ours works as well then.
Later in the afternoon today we can do that.
Yeah, that'd be helpful.
Anyone else
Okay.
have inputs?
Okay.
I mean, I'm almost about to fill the data sheet,
Okay.
so I can.
No problem. You can go ahead, Rajat.
Yeah.
Go on.
Okay.
Where is he based?
Where are you based, Rajat?
Yeah, I'm from Bhopal.
Bhopal. Okay.
Yeah. So I hope you can see the machine.
Yeah.
Yeah, we can.
So yeah, I'll just go from the beginning. So this is a compressor 1.5 H. Yeah, this is a compressor. It's a 1 HP, around 550 watt. That's what the
1 HP should be about 750 watts.
yeah 750. Sorry. So there's a cooling fan, and then the air goes in to this coil. This is around 1, 2, 3, 6, 9, 12. This is 12. Number of turns is 12, and this diameter is around 8 mm. And then the air is getting cooled. It comes to the regulator, and then it gets to the valve. So what we are using is two 3x2 valves, one equalization valve, and this is the RO canister, same old 20-inch canister, 20-inch, and the diameter is around 4 inches. This is the surge tank, 10 inches across 4 inches. So right now, what we are getting is around 66%, and that 66% of purity, and that we are getting when we are having a very simple code. For example, there is no equalization valve. There is this pressure goes up, and then this pressure goes down. Then this goes up, and then this goes down. So it's a very simple code, on-off code. So with that code, we are getting 66%. And when we switch on the equalization valve, so then we our percentage drops to around 40 something.
Wow.
So yeah. So basically, using the oxygate logic, we are getting approx 40. And if we use our
Orifices
simple
or
logic,
without orifices?
sorry,
Are you using orifices or no?
orifices. Orifices लगाएंगे. Yeah, so we are using orifices, and the dimensions are across like 1.6 diameter and 7 length.
Okay.
Yeah.
And you're not using any moisture separator after the coil. Is that right?
Moisture separator, like there is a filter regulator, which is this one. And there is no alumina or
Yeah, that's
silica.
not-
What's the ambient humidity in Bhopal?
What's the ambient humidity in Bhopal?
So humidity is around 50%.
Okay.
Okay,
But
that's,
you still need
but
something to.
yeah, you'll still need like at least a moisture separator. Otherwise, you'll short your zeolite pretty soon.
So after the coil, you get moisture, you have to remove it.
Yeah,
okay.
after the coil, what's going to happen is that the air is going to cool down, but you'll still have a lot of moisture and water in the air. That has to be removed before it goes into your zeolite. So for that, you need a moisture separator to the minimum.
Okay.
Just-
So
Hey, wanted to add to that. So even with our 3 kgs of alumina, we were seeing, and we're running it in a pretty relatively dry AC office environment. Within like 4 or 5 hours of running, we're like pretty saturated. Like we can easily open up the can and pull out like half a liter of water, almost like 300-400 ml of water comes out. The beads are very wet, so we need to actually let them dry before we can reuse that. So yeah, that is definitely something even in 50% humidity you have to consider. And so one thing we also wanted to ask everyone is what sort of what's a good way to recharge or have some sort of renewable desiccant. There was one membrane filter which someone had suggested to me. So that is something that looks like it actively cleans itself with the pressurized air. But if you were to use like silica or alumina, then how do you like in, let's say if you make a product and you give it to a hospital to use, you can't expect them to open up the whole thing and recharge the alumina. So that's also something to think about.
As much before it goes into desiccant tank.
Yeah, the trick is to try and remove as much before it goes into the desiccant tank. So that's what we're trying to do with the moisture separator and the cooling coil. And we're talking to a few more people to try and understand how we can maybe play around with the timing and or a chiller or a few things to remove it without a desiccant, because the desiccant will have to be replaced and will have to be something which is going to be a perishable that will constantly have to be replaced.
So
Especially-
easiest way to remove moisture is to give it thermal shock using a chiller or something like that. So all the
Easiest, Anul
moisture
is saying,
turns into water, basically.
yeah, what Anul is saying is that the easiest way to remove moisture is a thermal shock, which is chill the air instantly. That will remove all the moisture from the air. So
Condense it, then
condense
you have
it.
to remove
Yeah,
it
that,
somehow.
so it will condense it. That's what the coils are doing, and then you have to remove it. To remove it, you'll need the moisture separator.
Yeah.
I also have something to add. So you can also add a thermal expansion valve, which is to give that shock. If you guys have tried, Anul.
No, we haven't. You have some link or something you can share?
Yeah. So yeah, sure, I'll do that. And this is what they used in chiller plants to remove humidity.
Also, Krishna, have you sent your the moisture separator?
No, not yet.
Okay.
The same issue persists.
Done.
Okay.
Yeah. And also I have a question. So what's the pressure you get? I mean, you are using per sieve, Rajat, because I see you are also using the canisters, right? Oro canisters.
yeah. So we are getting around 30 psi per sieve, and in the storage it's around 10 to 15.
PSI is how many bar? 1 bar, 1.2.
Yeah, I get
30
confused.
PSI, how many bar?
Bars.
Sorry.
PSI.
PSI to bar.
No, we're just converting 30 psi to bar. How much is that in bars?
So
Yeah, it's 2 bars.
1.2. 1.12.
Yeah.
Okay.
I guess
Rajat,
it's 2 bars.
are you using a tank? Are you using a tank?
No.
So a tank usually does remove a lot of moisture.
But it comes through it.
Yeah.
You still need a moisture separator. It doesn't really, it does separate it. I mean, it's there, but it comes out in the, I mean, you can feel the moisture coming out. Your moisture concentration is the same.
So
So
Yeah.
tank does really help.
one question I had that Krishna, what are your cycle timings? So for us, it's working around like 13 seconds per sieve, charging, discharging.
That's
That
pretty long.
That's a lot.
yeah.
Yeah.
So we try.
Mm.
Yeah.
Yeah, I mean, I haven't measured the timing actually.
No, I mean in your code,
Usually
like
5 to 10 seconds is the usual PSA cycle
So-
for this kind of sizes.
I think it's around 8 seconds for me.
8 seconds.
Yeah, that's what Anul is saying. It should be between 5 and 10 seconds.
No, Anul, it should depend on L by D ratio. Like there are many factors, the timing. Like initially when I achieved 80% at 5-6 LPM from 1.6 mm sodium based zeolite. So my timings were around this only. So this is an interplay of many parameters.
Yeah, of course, but given 0.4 or whatever 0.8 size you're using, and given these canister sizes, I was
No,
assuming
I've gone through Rajat's timing and like the amount of zeolite also depends on the timing. So you're getting it, the purging and all that. So
right.
the volume that he's using is quite large.
Okay.
So in order to sieve that, in order to purge and do all that, the timings are high.
Okay.
So if Krishna is also using the same canisters, I guess Krishna, your zeolite is 0.4 mm.
Yes.
So then our volumes are like, or zeolite amount would be like kind of similar.
Yeah.
Okay. So
And also, Rajat, I just want to ask, like, how are you sealing it? Because I'm having air leaks at the lid.
okay, so what we have used is I can show you. If you can see, this is a Teflon over here.
Okay.
And like we packed it very like strongly. We use some hammer to pack it. So the leaks are not there right now. We used to have leaks, but right now there are no leaks.
Okay. So,
But-
when you mean Teflon, is it like Teflon tapes? Like-
yeah, it's a Teflon tape. Yeah.
On the top.
Okay.
So maybe Krishna, you like we can sync up later, like offline about the pressure timings and all that. So apart from this, there is one more thing I like to show. So this is yeah. So this is my other machine which I have set up. So this uses this 1.5 HP compressor, and this is a cooling coil around 14 turns and 8 mm dia. So this goes to this humidifier. So it like collects up until like this much amount of water, which is quite a lot. And after that, it goes directly to this activated alumna. So basically, I have made a 5-inch bottle size of like 5-inch length and around 2.5-inch diameter. This much alumna is there just right before the zeolite. Okay. So what happens is this gets pressured up, and then when it like depressurizes, so the alumna is also part of the same PSA. So using that setup, so this is the alumna, this is the zeolite, this is the surge tank. The other sieve was here, but it's not there right now. We just removed it. So I was trying this setup, and what I'm able to get is around 60% right now. So like yeah, so the total amount of zeolite I'm using is around 1.5 kg. And yeah, so the timings are also around like 4 seconds with the equalization valves on. It's kind of similar to the oxykit timings. So I'm not sure like how to increase it because this zeolite is like 0.4 mm sodium based that becomes zeolite. So any suggestion in that regard would be helpful.
Try increasing pressure. And maybe
Yeah, pressure
pumps in parallel. Both
yeah,
your
pressure is around 2.5 bar, which is around 50 psi. I would say.
And is that constant or is that going down when you turn it on?
Yeah, so when I depressurize it, it goes to 0.
So pressure is there. And what zeolite are you using? 13x.
Yeah, 13x, yeah. So it's the 0.4 mm size, 13x zeolite. Supplier is B Chems.
Okay.
Because if you remember when we were using the 13x
Yeah.
with the PVC seals, our seals we were going up to about 3 bar pressure inside the seal.
Yeah.
The compressor will bring about 4 bar roughly.
So when we were using plastic sieves, what Anul is saying is that we were reaching about 4 to 5 bar from the compressor, and the sieves were going up to 3 bar.
3 bar.
2.5 to 3 bar.
75%.
And we were getting about 75% purity. Then we changed to the aluminum sieves. And with low pressure, we managed to we were getting 90 plus. So what we sort of, one of the things that we concluded in the PVC sieves is that if there is too much air gap at the bottom and the top because of the reducers and the construction, that also there's a lot of air that gets stuck over there and that pressurizes.
Okay.
Could you elaborate the last part?
Saying the construction of the sieves when it comes to the PVC ones, if there is too much air gaps on the top and the bottom, that also leads to not getting reduces the efficiency.
So like when the air is coming from like 1/4 inch and you're expanding it to 3 inch or whatever that is, so how exactly that transition is happening? And you're telling there should be no that should be a sudden transition or what?
Yes, it should be a sudden transition, right?
Also with the aluminum seals, we use variable hole sizes.
It is like a frustum. You're creating something of a frustum, like you're not using a sudden.
So we're using, especially the acrylic piece or the drain cover that we use inside with the N95 filter. What we've done over there is that we haven't used consistent holes. So the holes in the center are smaller, while the holes on the outer side of the surface are larger. So that air sort of dissipates.
So the logic behind that is that Vinod told me that so that evenly distribution of air occurs. Okay, yes. That is different. I'm asking something else. I'm asking when you're converting the air from 1/4 or whatever 3/8 size to 3 inch. So is that transition sudden or like are you using something conical frustum sort of a thing to do that, or
it's sudden? In the aluminum, it's sudden. And so in the plastic, there was a little bit of sort of stepwise.
Conical. There was a gradation, and your conclusion is that your finding is that we should not use that.
But the reason is that in the aluminum, the change is sudden. However, there is no gap compared to in the PVC. When that gradation is happening, there is at least about empty void of about, let's say, at least 1 or 2 inches.
Yeah, roughly.
And that leads to the pressure
loss, I think.
Loss over there, or at least that air is being pressurized over there, but not really going inside the zeolite.
So like to conclude, it should be a sudden change. This is what you're telling?
Yeah, without any air gap. What we're saying is there shouldn't be any air gaps.
That means that it should be sudden, right?
So when we use the spring in the end cap to compress the steel mesh and that drain.
Yeah.
So that spring has like that is an empty space, right? So is that considered as an air gap?
Could be, but that's on the oxygen outlet side, right?
That's on the oxygen outlet side. Oxygen outside side, it should be okay. On the inlet side, there shouldn't be anything.
So I would like to add something here. When you do a sudden change, so what happens is that air expands, all right, and so water molecules, they also like condense. So at the lower level, you should use sacrificial, like if you're doing it a sudden change, then you need that a sacrificial, because the bottom layer would go waste if you're doing it suddenly when the air is expanding.
So with our moisture separation system, with the desiccant and that, we are getting under 10% humidity. So
Going into the sieve.
going into the sieve. So hence, I don't think we have too much of a sacrificial layer.
All right.
Yeah, I would like to add something.
Yep.
Yeah. So like you said, you're using aluminum pipes wherein you are putting the zeolite. So we are using the PVC pipes, which is similar in structure. And this is how we have put this is the entry point, and this is how we have put the mesh.
Got you.
And then we use this metal plate, this MS, we'll paint it to avoid oxidation. And then we directly put it here. So I guess this completely removes the air gap at the bottom.
That's perfect.
Yeah, that's good. Yes, that's perfect.
good. Yeah.
That's the right way, right?
Yeah.
Yeah.
That's a better way to do it. No gap.
Yeah. So, but in this case, these holes, they are redundant because air will directly go from this center hole, right?
Yeah.
Because,
The center one has smaller holes.
No, I have a solution for that. Wait, is my Jamboard visible to everyone?
No.
Wait, this is for rough work, so like.
Can't see anything.
Wait,
Can't see your Jamboard.
I'm sending you the link.
One second. Let me see. Screen share. Okay, check. Screen share should be enabled now for everyone.
Yeah, wait, do I have that?
but yeah, my question is, so if we are using this configuration, then we don't need the aluminum pipes, right? You can go ahead with the PVC pipes also.
Yeah, of course. They're much cheaper as well.
Yeah, it should work.
So like, can you guys like click on the kya kehte hain, Jamboard? Is it there?
In the chat.
The first page. This is this thing that I'm moving right now. Mind the rough work here. So this is what these people are doing, professional people. So the air is coming in.
The Jamboard isn't visible. Kahan pe kar rahe hain?
Channels for the air to flow.
Yeah, so this is how kya kehte hain,
Okay.
the air is getting dispersed
Okay.
evenly. Like, is it visible to everyone?
Yeah.
Anul?
Makes sense, yeah.
Makes sense. But in the Chinese one that we saw, there is none of these though. Right?
This is from the WHO's kya kehte hain, one of the WHO's approved on concentrator. So this is what these people are doing.
Gotcha.
Yeah, I mean, if you're anyway CNC machining the thing, you might as well add this. It's not a
Yeah.
big thing to do that. Yeah, you can try this as well.
Okay.
All right. Okay, who's next?
Yeah, I'll go next.
Sure.
So I'll just show the machine. This is my first time that I am introducing. So my name is Ankit. We are a team from Surat, and Vishal is my teammate. He's also online. So this is our device.
Where are you guys based?
Surat. We haven't registered our lab, so we are just individuals working on the device.
Okay.
Okay, so this is our sieve. We are using lithium sieves, lithium zeolite. This is from AGC Chemicals, Chalon. So each canister has 1.4 kg lithium zeolite. I know we have over-designed, but this is how it is. And we have 100% ensured that there is no air gap. We have ensured that there's no leakages. All those things are taken care of. And right now we have 1 HP compressors, 2 of them, but we are not using those. We have an industry grade compressor with a very efficient air cooler also.
Wow.
And we are taking air from that and feeding it inside this hidden moisture separator. But the air is so dry that we don't even see one single droplet of water. It's very, very dry because it's an industry grade air cooler. And
Can you
Sorry?
show us your compressor?
Or your industry?
it's actually outside. So we have a large factory and we use it commercially. We have 7 compressors here
Wow.
and we are directly taking it from the main line just for the purpose of experimentation. So we know that the moisture part has been taken care of. And then we feed it inside this air filter. Again, there's no moisture whatsoever. And then we have these solenoids. And then it goes inside this canisters. And then we have removed the equalization valve because during the timing, permutation combination, we saw that it wasn't efficient at all, the equalization valve. We have the orifices, 1.5 mm internal diameter, 7 mm, similar to oxygen specification. This is the NRV, and this is the surge tank, about 800 ml. And then we have the flow meter here, and then we get the output. So right now we are getting at 6 LPM about 88% O2 concentration.
Nice.
But as soon as we increase the LPM to 10, the concentration goes down to 70%. So we're not able to figure out what to change next.
What are your input pressure and sieve tank pressures?
Input pressure fluctuates between 2 to 3 bar, and at the sieve, the maximum air pressure goes up to 2.5 bar.
I need to increase that quite a bit, I think, at least up to 3 bar.
You can try and increase that up to 3 bar.
Even for lithium zeolite, because I heard that for lithium zeolite, we don't need as much pressure.
That high.
Yeah.
Actually, with lithium, we're not going that high. With lithium, we're getting it at just about 1.5 bar. So 2.5 bar is pretty good.
Yeah.
Is your lithium tightly packed?
Yeah, very, very tight. I mean, the spring that we are using, I think we are giving around 60 to 70 kilogram force. It's very packed. If we hammer, the zeolite might start breaking off.
What kind of timing are you using? What's your timing cycle?
Timing 8 seconds is the feed burst time, and 0 for equalization because we are not doing that.
So we used a slight gap over there, about 200 milliseconds for the equalization valve.
So we used about 200 milliseconds for the equalization valve,
Even though it's not connected.
Yeah, we did that. We also had the configuration where we used the equalization valve. We had 250 milliseconds each for equalization and pre-filling, but that was redundant. We didn't get any. The results didn't improve.
100 milliseconds.
We also tried with 500 milliseconds as the equalization time, where we were opening the equalization wall for 500 milliseconds, and still the result was same, around 88-90% is what we could get max for 5 LPM.
Have you tried without orifices?
Have you tried without orifices?
Yeah, without orifices, it goes down to 35% oxygen level.
Wow, that's surprising. How are we getting what we're getting?
I don't know. I think without orifices, how are you guys working? I'm really surprised. How is it working?
Well, I just asked him the same thing as to how come we are getting what we are getting.
Yeah, we're not using any orifices, just going directly out into the system.
So when we put the orifices, the pressure in the sieve tank was just oscillating between 1 and 1.5 bar, even though the feed pressure was 3 bars, and the O2 level concentration dropped 35%. And the moment we put the orifice back, again we were playing at 85 and 90%.
90 with our setup, right?
Ankit, have you tried lower LPMs, like 4 LPM, and what concentration you get for that?
Yeah, the moment we start reducing the output LPM, the concentration starts rising.
So where do you see 95%? Is it like 5, 4 LPM?
3-4 LPM, we start seeing 93-94%.
Do you think maybe the amount of zeolite you're using is not enough?
I think it's too much, 1.4 kg per canister.
Oh, never mind. Yeah, that should be more than enough. Yeah. But that could be one reason, like, I don't know why, but if you're if everything else in your circuit is working, it could be the amount of zeolite. Maybe for some reason it's deteriorated a little bit. But yeah, that's one potential issue because everything else in the circuit seems to be working.
There seems to be no humidity, right? So zeolite should be fine, technically.
So Ankit, you need to increase the timing or decrease the क्या कहते हैं, the zeolite concentration, the amount of zeolite that you're using, because like the logic is simple. Like if you have more of zeolite, so the volume is large, uh, so you need more timing to purge and to produce and to charge that. So what people are using, so there's two things. Like if you're using lithium, there's an entirely different thing. You go bigger and bigger. All right. If you're using lithium, you reduce everything to like a ratio 1:2.
Yeah, so that's what we'll try next. We'll try to reduce the lithium zeolite content. But timings we have increased to 10 seconds also, but the results started going down. The concentration started going down. So we found out that 8 seconds was the optimal time.
This
But
is the active charging time, 8
yeah,
seconds.
charging and purging time, 8 seconds.
And the equalize and the like
So
only
like,
one
we were
time.
going for 250 milliseconds and 500 milliseconds, but nothing was changing. So we removed it altogether.
That's pretty odd.
So right now we are getting 88%, 85 to 88% at 6 LPM with this configuration.
So how's the swing taking place using the orifices?
Yeah, we're using the orifices.
So orifices compensate for the other timing. So you understand that.
Yeah,
If you're
yeah,
using, so if you're using the orifices, what happens is that the initial active or charge time gets divided. Half of the air goes to the to the other cans also, or other towers also. So
Yeah,
that is happening parallelly.
Yeah,
So in order to like get to the right timing and all that, you need to have a consistent, like everyone should talk along with their क्या कहते हैं, pneumatic structures. Like giving timing is like giving half information.
So next up, we'll try reducing the amount of zeolite. But what else can we try? Now, what has the Goa team? What has worked for you guys?
We're trying to think what else is different in ours compared to yours.
Thinking.
Yeah, but yeah, can't figure out.
By the way, Ankit, what is the
Save.
Let's share our
inlet temperature?
tomorrow.
Yeah, this is our save. It's the same. Packed with lithium-based zeolite. We can show you the system, but we're just trying to figure out ourselves.
So which company zeolite are you guys using?
Huh?
Which company? Lithium zeolite?
So
This is Chinese.
We don't have a data sheet on it, unfortunately.
We don't have the data sheet. It's a
Our
Chinese
friends sent
one.
it.
Nitroxy.
No, we're
No,
not
no.
using nitroxy. This
What's
is
the
We can.
came without a proper data sheet, but it's 22% absorption.
And what's the weight per canister that you guys are using?
1
Not a
kg.
kilo, but 900 and some odd grams.
Per canister.
Yeah.
Yeah.
What are your timings?
Huh?
Timing, speed, source time, speed and burst timing.
4 to 5 seconds for the production cycle. And about 100 milliseconds each for the purge and equalization, but the valve is not used. It's just introduced the delay between the switchover between A to B. That's all.
And for lithium one, the feed pressure is 1.5 bar, you said.
No, we are working at around between 2.5 to 3 bar on the input side.
Does the input side meter reading oscillate during the feed cycle?
No.
It doesn't, because we see that when
No,
purging starts, the pressure drops all of a sudden in the meter reading.
it does.
That's right.
But that's why I said it goes between 3 to 2.5. That's the drop we get.
Okay.
Yeah.
You guys are getting what, 15 LPM at 90%.
No, not 15, about 8 to 10 LPM.
Yeah, at 10 it starts dropping.
Yeah.
At 8 we are above 90%. At 10 it starts to drop. So
we think we might also be measuring the oxygen in the sensor in a wrong manner. Can you show how you guys are measuring it and how you guys are feeding the oxygen inside the sensor?
Yeah, I mean, we
The OM202 sensor, it does not have an outlet. All the oxygen bounces off.
Come, we'll take you to the lab.
So you need to make a manifold for that. You need to like either 3D print something, or so you need to keep the oxygen sensor like in perpendicular to your air.
A T.
Yeah,
A T.
Yeah, T.
Venturi.
Yeah, so you need to keep it open to ambient or something on the other side.
So I got that, but my point is, so the air going inside the sensor has to come out from somewhere, right? So where is it coming out from?
It doesn't.
It is a
it
T,
doesn't.
na? So like if you imagine a T.
अगर T है तो
on the
अगर T है तो T तो ब्लॉक हो जाएगा ना, वहाँ जाएगा ही नहीं और है जहाँ जो पहले से ऑक्सीजन वो पड़ा रहेगा अंदर.
नहीं यार, मतलब ऐसे समझना कि एक पाइप जा रही है और उसके ऊपर आपने कुछ लगा दिया है. How do I explain this?
Here's a setup. This is a low pressure regulator. This one. That goes to a flow meter, and that's the output oxygen. But here we have a T, and on that T we have a sensor connected, and the output is a small bleed valve. So we have a small amount of oxygen coming out of here.
So this bleed valve is almost closed, just like you can't even feel it, just about that much oxygen coming out.
So most of it goes out here, and a very small amount goes out through here.
Okay, this helps. Okay, fine. I got it.
Yeah, Anul, can you explain that again, yeah? Because I guess you would be getting high pressure while measuring this.
No, because this circuit is open.
This circuit is open. So
from the starting, from where the air is coming in.
Yeah, let me speak for Anul. So this is the low pressure regulator.
Yep.
This is coming in from the surge tank. So surge tank comes into the low pressure regulator. From the low pressure regulator, the straight line is going into the flow, the rotameter.
20 LPM.
All right. This is all at high pressure, hai na? The high pressurized air. All right.
But there is a T in the middle, right after, between the low pressure regulator and the rotameter. There is a T, and that goes into the oxygen sensor, and then with a bleed valve at the end. Over here, we're able to control how much of this air actually comes through this system and into the oxygen, basically.
Yeah.
So we reduce this all the way down so that very less air actually escapes this point.
So you are actually increasing the pressure of while measuring it, yeah. So this would increase. This would increase your purity level.
You're not getting it. This is adjusting the flow, not the pressure.
It's not adjusting the pressure, it's just adjusting the flow because
it's open at this end, it's open at this end.
It's open completely at this end.
So when you have an open system, you don't have pressure, you have flows.
So if I'm asking ki at what pressure is this?
There isn't a pressure because it's an open system.
Ambient pressure and flow rate, and the flow rate through which this air is passing. The oxygen sensor. Around the oxygen sensor, what is the flow rate?
100 ml.
Yeah, 100 ml per minute or something.
Per minute. So very less coming out of here. So that's all you're adjusting because this is an open system. All the air is actually going through this into this guy. So only very less air is going through this actually. So this is the right way of measuring it according to like all the documentation that we read. That very less air flow needs to actually go into your oxygen sensor. Your oxygen sensors cannot function at high flow rates.
Like we have tried all the combinations.
You've tried everything.
Directly, putting it after the flow meter, putting it before the regulator. We have tried all of those.
Yeah,
this is what works.
This is what works because if you put it right here, let's say, if I put this like in a direct line, then you have very high flow rates. Then there's going to be supreme amount of fluctuations and you won't get a consistent reading at all. Another thing is that's very bad for your oxygen sensor, because your oxygen sensor is not supposed to be used at
Suited for high.
flow rates and pressures. Yes.
Yeah.
I have a question, guys. So, how are you maintaining a pressure? Like, because I read somewhere, maybe in the group, that it needs like at least 1 bar. I mean, less than 1 bar is something that it won't give reading, and above 1 bar is dangerous for the sensor. How are you maintaining that?
So, Krishna, that's the thing. Pressure is let's say, is a result of an enclosed system,
Okay.
and flow is a result of an open system. Right, so they are kind of interrelated in that sense. If you have an enclosed, which is why like a compressor will give 8 bar at 0 RPM, right? Because it's enclosed. But when you start increasing the flow, the pressure drops down.
Correct.
There is a relationship between the two for that. So in this case, it's an open system. If I block the output that's coming into the flow rotameter, for example, then the pressure builds up.
Then you'll be able to see pressure build up over here.
Yeah.
But if this is open, this is at 0 pressure almost.
Yeah, it's just flowing out.
It's just flowing out. So the pressure gauge is almost at 0.
Pretty much.
So, so when you directly connect the compressor, the air coming from the compressor to this, you're getting 21%, 20.9%. Na?
Yeah, of course. Yeah. Once we remove this and just measure it in ambient air.
No, in the ambient air, you won't have the same. So what you do is that from where the air is coming, na, just put your compressor out there in the same setup, just replace that with the external compressive air so that you can have like everything is same, and then you measure it accordingly also.
But what's the point?
The point is like so like you normally when you calibrate it around the atmospheric thing, all right, when the flow is even like 0.
Yeah.
And when you put it in this, there might be some flow and something. So it is a precaution to remove all the errors. Like just change the setting, like from the compressor air, just pass it into this and see if it is getting 20.9 or not.
Yeah, I mean, we have one sensor and 2 reference meters, so we are actually able to measure pretty accurately.
Sorry to interrupt actually. What I think is how you have connected this is the right way.
Huh?
Sorry?
The way which you have connected, this is the right way.
Okay, good to know that.
Yeah. Because just now I received one state from forensics oxygen analyzer.
Okay.
And I'm just connected it to 5 LPM. The only thing which I found is they are given one input. What you connected is I have connected the input 5 LPM directly to it. And what is happening is through the bleed port, it is able to bleed the air, the oxygen. So the only thing, if you have a bleed on the line, then it is okay.
Yeah, having a bleed is important.
So that's the important part of the whole thing.
Yeah. Then what you're getting from that sensor should be more or less an accurate value.
I mean, you can even put a rotameter here, which is set to a very low value, like 1/10 or 1/100th of this.
Yeah, because what the engineer told us, it doesn't even need like 0.3 LPM also. And what he told, the NVTech sensor, the OM202, it already has a very small bleed in the sensor itself.
Yeah.
But when you put high pressure, that is when it goes out of range and all those things. So what he told, to put a bleed in the line so that the pressure doesn't affect the sensor. That is the only thing he told me. And to keep the LPM within 0.3 to 0.5 LPM. Even that he told it might be more.
Yeah. So yeah,
Guys, is there any other way than the rotameter to get the flow of like 0.3 to 0.5 LPM?
Bleed valve.
You can use a bleed valve, but you still have to measure it. This way, it allows you to actually view what your flow rate is. Here, you can't really know exactly what your flow rate is.
but we just keep it over.
One thing what you can do is if you have a smaller flow meter like 0 to 5 liter, you connect this bleed valve, the whatever needle valve is you connect to that flow meter and you try to set that flow.
Hey, can you give us a walkthrough of your device since you're here?
Yeah. So the sieves are out right now, but I can show you around. So that's the compressor. That's the single 1 horsepower compressor. So we're switching between this one, and we're also experimenting with this one. So this one is better. However, the tank is not really required. So, but we don't
Not
have.
audible, not audible.
Can you hear me? Can you hear me?
Video is paused.
There's a video getting stuck. Your network's a little slow in this area.
Yeah, the network is a little slow. That's why I was going back. Is it better?
So guys, everyone else, please switch off your video. So bandwidth is better.
Is it better now?
It's fine now.
Okay, so we're basically using 2 heads instead of 1 head, but both 750 watts. So 2 HP in parallel. So 1 and 2. Okay, that's what we're primarily using. From here, the air goes into coil number 1. So this is a helical structure coil. Can you guys hear that?
Yes.
Yes.
Okay, that's the first coil that it goes through. Then from the first coil, it goes into the second coil. That's the second coil. That's an inverted helical structure. And it goes through the copper coil. There are 2 fans at the bottom that are pulling these copper coils. Okay.
Yep.
From here, we go into a moisture separator at the back. Inside over there's a moisture separator that separates out the moisture. From the moisture separator, that's where we are able to remove most of the water, but we are still left with about 40% humidity. And Goa, the ambient humidity is around 80%. So from 80, we go down to 40 over there. Then we have a high pressure flow regulator valve. From the high pressure flow regulator valve, it goes into the desiccant. This is the desiccant chamber where we're using alumina based 1 to 2 mm bead size zeolite. And then from the exit of that, we have another T where we have another bleed valve where we open it out to just measure the humidity of air. Over here, after the desiccant, we get around 5%, 4 to 5% humidity. So that's pretty good. From there, sorry.
Hey, just a quick question. So you're using the zeolite as a desiccant?
We're using alumina-based zeolite as a desiccant, yes.
Oh, alumina-based zeolite, and that's something you found locally?
Yeah, we got it from a dive shop. So
and how do you
it's quite cheap.
recharge that?
400 rupees a pack.
And then is there a way to like regenerate it, or is it just thrown away?
You can get this from Silicon or Sorbide in Baroda, and it's what do you call readily available at both, and less than 500 rupees a kilo. It's readily available. There's no.
How is it different from activated alumina? The larger beads.
It has more absorption.
This one has more absorption for moisture, 25%
By weight.
by weight.
Are you guys regenerating it?
No, we haven't tried regenerating it yet because we don't have a vacuum-based heater.
Vacuum pump,
Yeah, but
No, I mean, did you guys try to put it in the PSA along with the zeolite, along with the sieves?
we haven't tried that yet. So we're just discarding it after a few days once humidity level starts going. So that's
What sensor are you using for measuring the relative humidity?
EST22.
Okay.
We also have a reference instrument, which is this guy. If you guys can see what a node is opening up, this is a professional instrument to be able to measure humidity.
Humidity and dew point.
And dew point. So we're using both those references, but this one is pretty accurate. It's not too bad.
Okay, thanks.
So how did you estimate the size of alumna zeolite? Like how much zeolite would you need?
Estimated.
We guesstimated
Yeah,
like
sure if it's the right
1
size.
kilo approximately.
Yeah.
Okay.
And then from there, let me just finish quickly and then I'll just go back into the other room. So we're from the desiccant chamber, it goes out into a T and then into the two walls.
And that's it.
That's it. Then after that, it goes into the two sieves. And just to correct, we are using orifices. We're
Yeah.
sorry about that.
Yeah.
We are using orifices, the same ones, the approximately 1.2 mm diameter hole
Yeah.
orifices. And from there, so two sieves. From there, with the orifices, we still have the orifice system. So we were confused about that. And then we have a small little surge that you can see over here. This little surge tank, it's a 300 ml surge tank right here.
Can you please show the orifices because it was not visible during your presentation?
Yeah,
And can you also confirm, do you have the equalization valve or no? That's definitely not there.
That's definitely not there. Yeah, it's kept right here. So we've taken it out. So we're not using that. We're using, there is a surge tank right here. From the surge tank, it's going directly into the regulator, which is right here. The low pressure regulator, and then the oxygen and the flow meter. The orifices, I will just show you in a second.
Just wanted to show them this hack for making really nice connections to the copper coil.
Yeah.
These brass connections, they go pretty well on these, on the copper coil. And then we can just add solder over here. We use the Dremel, which is lying there.
Yeah, we just use a butane torch.
Butane torch.
And some
And,
solder.
That's it.
And you can see the wait, yeah, right here, how we braise them.
Yeah.
So this is quite a good seal that you get.
Yeah.
So what's the approximate length of total copper you are using?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I mean in feet.
So twice of the oxycate. So we basically the 12 coil system. We're using 2 of those 12 coil systems.
Okay. So basically something around 44 feet. Is that correct?
Yeah, close to that. We can measure the exact amount. We didn't really measure it, but we should. We took the entire coil. One of these, we use the entire coil. How much is the new ones that are packed? How many meters in there?
Did you feel the need to like use so much copper? As in, is it because you're using 2 compressors? There is a lot of heat generated.
Yeah, it's giving us good results. It's definitely taking out a lot of the moisture, and plus the air is pretty cold when it comes out. So yes. One coil, it's still a little warm. After 2 coils, it's definitely cold.
So any idea what's the temperature difference from the inlet, like the inlet of and the outlet of the copper?
Yeah, something like that.
16 degrees difference. Is what
16. So are you guys crossing the dew point? Any idea?
Not too sure. We still have to run those tests though.
We still.
Sorry? Didn't hear you.
No,
we're
not too sure.
We're not sure about that one. We can run that test.
We have to run those tests, yeah.
But yeah, we primarily after the coils, we throw it into the moisture separator. That's where we collect most of the water.
Yeah.
And then we throw it into the desiccant where we collect the rest of it. So after the moisture separator, we're down to about less than 40%, around 37, 36, somewhere over there on average. And then after the desiccant takes away all of that. So we're down to about 5%.
That range.
Great.
Yeah. Any other questions about the system before we go back?
So you're using 3 orifices, huh?
We're using, no, 2 orifices.
Okay.
2. One on each end of the sieve. We tried without. And I don't remember it to be that bad.
The oxykit uses 3.
The oxykit is 3. We're using 2. Just at the end of the sieves.
Do you have the make and like the? Can you show the moisture separator you're using? Like
Before desiccant.
before the desiccant?
This is this one.
Okay.
FRL unit. This is an FRL unit, right?
Waiting for the auto.
We're waiting for the auto one from the one that Chennai is using, Dverse Labs, Krishna.
Okay.
But this is a manual one, so it doesn't auto drain. So
Oh, there is one that auto drains that cannot drain.
no, this doesn't auto drain. So you have to like when the system turns on, it auto drains. But when the system is running, it doesn't auto drain.
So this hydent moisture separator, that's the one that can auto drain.
Yeah.
True.
Okay. And how much are these?
800 rupees? No.
I haven't seen any other invoices, so.
Okay.
Just check again, but it's there in the BOM with the costing.
All right. All right.
Yeah, one more question. Like the orifice using, is it like a fabricated one or is it like an off the shelf?
It's a machine brass one, yes.
Okay. So it's something that you fabricated?
Yes.
Can you show it, the part?
Yeah. I can show it. One second. It's inside it. A long stick or something to push it out. I'll need something to push it out. 1 second. Do you have something long to push it out? Is there one here? You can see this inside the pipe. It's a small orifice. I can share all the details for this. I'll try and take this out.
Yeah, sure.
Yeah.
Got it. Yeah. Thanks, man.
So by the way, what's the approximate pressure in the surge tank?
Again, pressure gauge is there at all.
We don't have a
I'm guessing around 2 bar.
No, not 2 bar. Not more than 1 bar. We want it over 0.5 to 1 bar. But we can check.
You can check that.
So is it something like the pressure gauges reduce the efficiency? Like why do you guys remove it?
Actually, the 2 gauges, yeah, different readings both of them. So we are not sure how accurate
Yeah. So the 2 gauges that we have, they both show different readings. And that's why we won't show how accurate they are. So that's why we just remove them.
Okay, yeah. And yeah, I had this question. So does the size of the surge tank matters? Like if the surge tank is, let's say, 10 inches big, and if it is, let's say, 5 inches, so
to reach concentration after startup.
Yes. A smaller surge tank
Reaches faster.
is concentration faster. So we're using a 300 ml surge tank.
But it fluctuations. So some kind of
Yeah.
Balance point between
Yes. Yeah,
too small and too big.
true. It has to be just the right size depending on the LPM output. So
in the collective, someone told me that P by P naught ratio, that is the pressure in the towers to the pressure in the oxygen tank. should be close to 1. Like this also matters.
Okay, come again. What's the ratio?
The ratio to the tower,
Okay.
the zeolite tower, and the one in the oxygen tank. So this also matters, P by P naught ratio. Someone in the collective told me that.
And how much should it be?
A physicist, he told me it should be around 1. Should not be greater than, like, should be as close to as 1. We should not create more. Because half of the zeolite is filled, like the actual volume that is there, the left out volume in the tower should be same as the oxygen volume. So if you keep the volume of air constant, so that is the logic. Because we're filling the first tower with the zeolite, the amount of void that is there. The giveaway is that P by P naught, the pressure should be same.
Okay. Not too sure if I understood that well, but yeah, we can try and see what's the relationship if someone can light on this.
So, Abhimanyu, if the pressure in the surge tank is more than the sieve chamber, so what would be the problem? Because let's say if I'm using the non-returning valves in my system. So
Rajat, because I'm just referring it because I don't have the right knowledge, but this also matters, P by P naught.
Okay.
So my understanding is a bigger surge tank requires more time for the oxygen concentrator to reach declared output of 92 or whatever percent. A smaller one will reach faster, but it cannot take care of fluctuations in the output. So you'll have a more bobbing, let's say, rotameter. So there is some kind of a balance between the two which we have to achieve. The number I'm not too sure, but my guesstimate is you need to have something that about half the size of your sieve tank as your surge tank. But of course, I know physics to back it up. I mean, it's just something that I feel as a gut feeling as what the surge tank size should be.
I think it should be 1/4.
1/4. Okay.
It depends now. If you're using the the aluminum one, which are already very compacted, you could go for 1/2. But if you're using UPVC, they have all that air, the spring and all that. You getting that?
Does anyone remember what's the sieve size for the original oxykit and the surge tank length? How much is that ratio? We can figure that out. I think the surge tanks the sieves were around 17 inches, 18 inches, that's 1.5 feet. The surge tank was around 9 inches, that's about 200 mm. So 200 mm to whatever. Yeah, I think 1:4 might be the ratio for that, I guess. Okay, did we lose everyone on the call?
No.
There was kind of silence. Naveen's got something to say. Naveen? What's up? Naveen raised his hand.
Anything to say?
Nope, I guess not. All right, so
I had a question, just last question. So I was planning to use this as my end cap. So this is a nylon based material, and what I've done is there are threads inside it.
Okay.
And I'm using those pipes as my sieve chambers. I'm planning to use them. So what my question is, I heard that some people face some issues with nylon, removing at high pressures. So is that should that be a worry or is it not?
I'm not sure what's the compatibility between nylon and PVC in terms of stickiness. So sometimes that could be an issue. On the other hand, something like, for example, Delrin, that has got a very nice, let's say, you can use it with most of the metals or plastics, screwed parts, for example.
Okay.
We used Teflon for that, right? On the PVC.
Use Teflon on PVC, that worked. Yeah.
But Teflon on aluminum is a bad idea because then you can't open it.
Yeah.
It's shield shut.
Okay. So any idea about how nylon? How does it work at high pressures and high temperatures? Like, does it lose its grip?
No, I don't think it does. I mean, it's a fairly industrial material, so it's used in a lot of places. Right? So pressures aren't too high, temperatures aren't too high, so it shouldn't be a big problem. I guess the best bet is to try it out and report back on what your findings are, I guess.
Yeah, the problem with nylon is there will be a little bit of flex actually, which will cause your thread to slightly move under high pressure. That is why how it can come out. The one with the other material which I was referring to, what they are told, since its density is more, it doesn't have such a flex, so it will not lose that thread. That is what they were telling.
Okay.
Plus nylon, normally nylon, what we see whenever we use a nylon, any bucket or anything, how much ever we press, it comes back to its original shape. So it has some sort of elasticity kind of thing. So that is what I feel. It is like the shape is getting changed during high pressure. That is how it is able to pull out of the thread.
I think which is why they have glass-filled nylon. And there are different grades in it, nylon 6, nylon 66, and so on. Which are different.
Yeah, glass fill might be a better choice, I think.
So
okay, yeah.
I'm not sure which kind of nylon he has, but I mean, it's worth giving it a shot to see what happens. But it's true, nylon does flex, so threading it and all might be a bit tricky in terms of getting the right pitch and so on.
Anul, what can you say about like we had that issue na, in case of like power fluctuation or in case like if the light goes down or so if you are using a tank, can that act as a safety measure? Because instead of giving a battery, it's better like if you give a tank, so mechanically it would keep the system running.
So
Yeah, sure.
what we so in terms of power loss, the thing is that the electronics needs to keep running. It doesn't matter about the tank because what happens is the tank will reduce pressure and it will go away, because if the system is running continuously, your pressure goes down from 8 bar, which is stored in the tank, down to 2 bar any which ways, depending on what kind of motors you have on the tank. So it's actually the tank is doing nothing apart from just taking in air and pushing it out. Because
Making it colder is what it does. So.
Making it colder is something that it definitely does.
Yeah.
Apart from that, the tank doesn't do much when it comes to holding pressure, because it's constantly
Flow rate is pretty high.
because our flow rate is quite high, and that's going to be in the case for all of us. Unless the tank is really, really big and you have really, really powerful motors, then you have some sort of back lag stored inside the tank.
Yeah.
But with a small tank, not much.
Not much.
Uh, Electronics, however, should have a backup or a UPS, right?
So like if I'm using it and suddenly if I'm a COVID patient, I'm using it, and if suddenly the power goes down,
yes.
So what then? Like, what's the use of? Everything fails now.
Yeah, that's why you need a genset backup or a inverter directly in the hospital, and most hospitals have that.
Yeah, it's a bigger problem to solve, which I think is not a part of the concentrator issue per se.
Yeah, you'll have to add like bigger
an electrical supply issue, which is not.
All right. So I was thinking if I could use a bigger tank, so that would help in that, at least for the crucial moments when the light. All right.
A few seconds or minutes at most, but not more than that really.
Maybe maximum a minute.
Yeah.
If you try, but not more than a minute.
All right. And one more thing. So earlier, while we were using sodium and everything, we were using oxykit as our benchmark. but now every one of us have shifted to lithium based, and so what is another benchmark for lithium? Like, do we have that also? Like, instead of
making one together. We're all making it as we speak. That's what we're doing.
So,
yeah, I think we don't have one really. So which is why
maybe these Chinese ones is a decent benchmark.
because we need to like have a Chinese or any lithium one as a benchmark, so that we can scale up from that direction also. We're coming from the top direction.
We do have a Chinese one over here that we sort of trying to study as well on the side.
Well, I had one Korean one that was giving with lithium 7 LPM to 10 LPM at around 95%.
95 10 LPM with the Chinese one too.
Yeah, 95 10 LPM with the Chinese one. But I'm curious about the flow meter as well. How accurate is their flow meter? I think the flow meter is also hacked.
Also, the oxyform one. Also, these people are using lithium, and the timing is also like. So we are using a different benchmark out there. When you coming down, so the oxyform people are also they're divide off any walls and all that, and the basic concept that they're using is somewhat in a different direction than the oxykit one.
Okay.
So we can use that also as the benchmark.
What's the name of the project? You said
Oxyform. These people, what they did was that they removed all the walls, all the electronic stuff, and they made a 3D printed cam wall, so that.
Group. Okay, got it. Yeah.
So.
Bharat
O2. But that design is a patented design from some Japanese company. So they did not make anything. They just copied that patented design, wherein you don't use electronics or the walls or anything. This happens when you go to the lithium one, because you don't need much walls and all that stuff.
Yeah, and it's very. The only thing is that you also have to really get the timing right.
But that is not customizable. That will be at the later stage. You can adopt that. Once you know what are your final timings and all that, then you could like.
Yeah, for prototyping, I don't think it's ideal because you are trying.
Not ideal.
Yeah, that's true.
Okay. So, any last few comments, because it's already 1:45. We've extended the call by almost half an hour.
We can repeat this again either tomorrow or after a few days if there are others who want to show off their systems.
Let's do it on Wednesday or Thursday.
Yeah.
Thursday.
Yeah.
Let's do it on Thursday again.
Okay, I think that works for everyone.
Okay. Great talking to everyone. Thank you guys. Let's get back to work and good luck.
Yeah, we'll have the engineering catch up sometime in the evenings, one of these days.
Yeah, and please fill up that form. I know it's lengthy, but to be able to understand what each of our systems are at, that will really help.
Yeah.
The guys from Cambridge are also trying to study those, and they will be also studying this call. So hopefully some good documentation will come out of the same.
Yep.
Okay, thanks everyone.
Bye.
Thank you.